Ben bir mühendisim. Ofiste, evde, yaşamın her alanındayım. Görülmeyen ama hissedilenim. Ben ne kadar görünmez olursam, projelerim o kadar başarıyla tasarlanmış ve uygulanmış demektir. Tıpkı sizi sizden fazla düşünen gizli bir kahraman gibi. Kahramanlık, kağıtla kalem bir araya geldiğinde geleceğe yön verebilecek kadar cesur olmaktır. Çünkü mühendislik, bilim ve doğa alanında tüm bilinenleri yine doğa ve insanlık için kullanmaktır. Tasarımda sadece estetiğin değil, sürdürülebilirlik, enerji verimliliği, çevre duyarlılığı gibi kavramların da altını çizmektir. Mühendislik, modern, konforlu ve doğaya saygı gösteren yenilikçi yaşam alanlarını hayal etmek ve gerçeğe dönüştürmektir. Gelecek kuşaklara yön vermektir. Binlerce yıl önce bir kıvılcımla yaratılan aydınlığı bugün tek bir tuşla milyonlarca insanın yaşadığı yerlere taşımaktır. Geceyi gündüze, soğuğu sıcağa, sıcağı soğuğa çevirebilmektir. İnsanlığın ihtiyaçlarını karşılamak için hayallerimizi gerçekleştirirken yanımızda TTMD vardı. 1992 yılında kurulduğundan bu yana çatısı altında güven bulduğumuz, etik değerlerin teşkili ve temel sorunların çözümü için birlikte çalıştığımız yol arkadaşımız. Farklı disiplinlerden gelen profesyonellerin ortak amaçlar için toplandığı TTMD, üyeler arasında iletişim ve tartışma ortamı yaratıyor, bilimsel ve teknolojik yayınlar yapıyor, üniversite, sanayi, işbirliğine destek veriyor, çevreci ve enerji verimli çözümlerin yaygınlaşmasını destekliyor, yurt dışındaki gelişmeleri izliyor ve sektörü yurt dışında temsil ediyor. Bizler tüm insanlığın iyi yaşam arayışına çözüm buluyoruz. Bizler yarınlarımızı şimdiden kuruyor ve daha sürdürülebilir bir dünya için çalışıyoruz. TTM'de 1992'den bugüne yaşam mekanlarında insanlığın konfor ihtiyaçlarını doğaya saygı göstererek sağlamak için var. Mühendislik mesleğini etik değerler doğrultusunda uygulamak için var. Türk Tesisat Mühendisleri Derneği. Gelin geleceği birlikte yaratalım.
Good morning, good afternoon, and wherever you are. Welcome to the webinar organized by TTMD, Turkish Society for HVAC and Sanitary Engineers, in collaboration with International Energy Agency Energy Storage, TCP. I'm Halime Paksoy from Çukurova University, Turkey, professor of chemistry department and the director of our Center for Environmental Research. I'm also the delegate for Turkey at Energy Storage TCP. I would like to start with some brief information on International Energy Agency and TCPs. We'll have a very short presentation for you now. International Energy Agency, or in short IEA, was founded in 1974 for long-term cooperation on energy R&D. At the beginning, it was only energy security that was of concern for IEA. Initially, sustainable supplies of oil as a result of crisis in 1970s. And later on, alternative sources of energy and energy conservation measures became important. And most recently, the climate crisis is also in the focus. Over 80 technology collaboration programs, in short, they're called TCPs, have been created over the almost 5 decades of technology collaboration with all stakeholders that include research, industry, policymakers, NGOs, and others. Today, there are 39 TCPs with representatives from 55 countries around the world and around 300 institutions, and with global network of thousands of experts. TTMD represents Turkey in 3 TCPs. IEA Energy Storage TCP, IEA Solar Heating and Cooling TCP, and IEA Energy in Building and Communities TCP. Today, we are organizing this webinar with Energy Storage TCP. Energy storage, you see the logo on the screen now, contributes to the transition toward a renewable energy system by the use of energy storage through joint research, design, and development since 1978. It's one of the earliest TCPs within IEA. Currently, there are 21 members from countries and different institutions, and have completed so far 36 tasks, or you can call them projects. And right now there are 9 ongoing tasks. You can reach the documents or related publications of IEA EC energy storage through this square code there, or the website address is given there. And you can also follow us at our LinkedIn address given here. That's all from the IEA energy storage, and let's now pass on to our webinar. This webinar coincides with the COP28 meeting that is taking place in Dubai. There has been a lot of media focus on especially the country with fossil fuel trade business hosting this organization. But it's most important of all, putting those discussions aside, COP28 may be one last opportunity for world leaders on deciding to ditch fossil fuels. And I would like to quote the director of International Energy Agency's, Mr. Fatih Birol's speech that was given at COP28. In his speech, quote, he said, "If renewable power capacity is tripled by 2030, we would deliver about a third of the emissions reductions needed this decade to move the world to a pathway aligned with 1.5 degrees Celsius scenario. Otherwise, we are running towards very dangerous levels of global warming, which is well above 2 degrees Celsius." So 2030 will be here in less than 7 years. Energy storage will be more important than ever if we really want to triple renewables capacity during these 7 years. So we must all ask, how affordable is this goal? So we will focus on this question today. And we have our distinguished speaker from Germany, Dr. Andreas Hauer. He will talk about economics of energy storage. Dr. Hauer is directing the Zeta A Bayern Research Center in Germany, and he also leads the Task 41 on this topic in IEA Energy Storage TCP, and he has other hats. Maybe he can tell us about them in his introduction. But before we start, I would like to ask you all, please use the chat section to send your question. During and after the presentation, we will have a Q&A session at the end of the presentation. Now the floor is all yours, Dr. Hauer. Please start by letting us know a little more about yourself.
Okay. Yeah, thank you very much, Halime, for the introduction. Well, you already said it. I try to share now my screen first. Okay, that's not good. Second. Okay. So I hope you can see now this the slide.
Yes, we can.
Perfect. Yeah, my name is Andreas Hauer. Yes, I'm head of this very small research institute. I'm also involved, as you heard, in the IEA energy storage TCP activities. And I'm also vice president of the German Energy Storage Association, which is an industrial association. So we have about 300 companies in Germany dealing with the topic of energy storage. And that is a little bit the background why we said it would be interesting to look at the economics of energy storage. And the question behind it is, of course, what is the value of energy storage? So let me start with my presentations. But first, I have to say I'm very happy that Halime asked me to give this presentation. So I'm really honored to be here and talk to you. Yeah, a brief overview. I will start with a basic definition. It sounds easy, but it's always very different to make something like a basic definition of energy storage. And then I will start talking about the economics, giving some examples, and then briefly introduce the different technologies of energy storage and have a look at the applications, because it's very important. Energy storage and real applications are have a very strong connection. I will give you some examples on energy efficiency and energy storage, on the integration of renewable energies, and then coming back to the economics and end up with some conclusions. So now for the basic definitions. What is energy storage? Big questions. So the basic definition sounds like this: an energy storage system can take up energy and deliver it at a later point in time. So that is very important, because sometimes we have a discussion about energy storage versus the, let's say, upgrade of the electricity grid or something like that. So energy storage can do this shift in time. That's very important. The storage process itself consists of 3 stages. We have the charging from a source to the storage, and then later we have the storage itself, keeping the energy in the storage, and then we have the discharging. And after the discharging, we can do it again and again and again. Second question, what is actually stored? We have different types, different forms of energy: electricity, heat, cold, mechanical energy, chemical energy, and so on. And the one which is taken up by the energy storage system is usually the one which is delivered. But sometimes we have cases where we transform it. For example, in the pumped hydro storage, we have electricity and we transform it into a potential energy, and then we retransform it into electricity. And sometimes we have a different input and a different output. So that means in some energy storage systems, the transformed energy type is the one delivered. For example, power to gas or power to heat. So we start with electricity, but we deliver in the end hydrogen. And the third point is, as I said before, the relation between energy storage system and the application. So it says the technical and economical requirements for an energy storage systems are determined by its actual applications within the energy system. Therefore, an evaluation and comparison of the energy storage technologies is only possible with respect to this application. So the application really is responsible for the technical requirements. So the type of energy, the storage capacity, the discharging, charging power, things like that. And also the economical environment. So the expected payback time, the price for delivered energy, all this depends on the real application. So 2 more points on this basic definition. I said it is about shifting energy in time, and in reality it means matching supply and demand. In the past, we had a system with a more or less constant supply from fossil fuel power plants, and then we had to match the, let's say, fluctuating demand. And then we had times where we had too much supply, and there we could use a storage, and then we could deliver energy from the storage to the peak demand, for example. Today, if we look at the renewable energy sources, we have fluctuating supply and we have a fluctuating demand. So that means a lot of fluctuation, and that means a lot of energy storage demand from first principle. Second point I want to make, in addition to the definition, is that we have a difference between power, energy per time, and energy itself. So sometimes we use energy storage in order to increase the power output. So we want a high power output, and sometimes we really store the energy. So we're looking for a huge amount of energy, and I have two examples here. One is a battery system used for charging infrastructure to deliver very high power output for fast charging. And that comes from the battery. And we have a fast discharging of the battery here. The battery, not the battery in the car, the battery you see in the picture here. And this battery has a very slow and constant charging. So that could avoid an upgrade, a necessary upgrade of the grid for fast charging infrastructure. So this is really about power, energy per time. And then another example where we really store a huge amount of energy, that's a seasonal hot water storage in Denmark, where we try to store heat from summer to winter. So that is really about energy, kilowatt hours here. Okay, now that was, let's say, kind of introduction, and now we come to the first part of the economics of energy storage. So it is a little bit what Halime said in the beginning, that we have a working group now on this question, economics of energy storage. And we started with some questions. We said, okay, what is the benefit of energy storage in the system? And from, let's say, things like the availability of energy and power in many applications and many technologies. And from this, we want to derive what is the value. So the question, how much would somebody pay for this benefit? And the third question is, who would pay for it? So if you can identify a party paying for this value, then you have a business case. And that is the crucial question in the end. Do we have a valid business case for a certain energy storage application? So what do we expect from energy storage? As I said, if we look at energy, we want to have an energy supply, a constant supply. We want to have maybe covered our peak demand by energy. We want to have an offline operation. So this is all about the energy supply. And then we have this question of power. Again, it's energy per time here. So it can be positive or negative. So if you look at your bathtub and you have a hot water storage, then it is about that you can fill your bathtub very quickly from this storage, much quicker than from any other energy supply. Or this example of the EV fast charging I talked about already. But if you look at grid services, sometimes it's important that you have kind of negative power capacity, that you can take electricity from the grid in a very short time, a lot of electrical energy. If you have, for example, a high input from renewables from a storm or something like that. So you see there are different things we expect from energy storage. So maybe we go a little bit more into the diversity of these benefits. From the availability of energy and power, we can derive some services we expect. One is called this big word, flexibility. I talked about grid services, so that energy storage is able to stabilize the electricity grid, for example. It is very important to integrate these fluctuating renewables into the system. Second point is reliability or security. So we can provide by storage an uninterruptible power supply, for example, things like that. Then a topic like mobility. So storages are able to drive electric vehicles, batteries, or batteries in mobile phones. Then autarky is an important point. So if we look at island solutions, self-sufficiency, and I think this list can be extracted here, so expanded. More points are possible. So now this was very, let's say, theoretical. I want to come to an example. So I have chosen a very, let's say, unusual example because it's easy to talk about a PV installation and a battery, but here I want to do something else. It is a power to cold energy storage within a refrigerator. So it is a very small phase change material, we call it. It's a latent cold storage. It is really small. It is integrated in a refrigerator, in a fridge. And we think that we have about, let's say, 20 million fridges in Germany. That's less than 50% of the households. So the idea is to create a dispatchable load within the electricity grid by using these cold storage. They transform electricity to cold. They all connected by a kind of intelligence. So I don't want to go into details here, but they all controlled. So that means I can, as a grid operator, for example, I could say, okay, and now I have too much electricity. I use maybe 10 millions of my fridges to charge my storage. And then at a later point, when it's not enough electricity in the system, I can take these fridges off the grid and they use their storage to provide cold production in the fridge. So you see here some details. The PCM cold storage can provide cold for 7 to 8 hours. It can be charged in 2 to 3 hours. And the cost of this, let's say, small units, in some of the pictures down there, you see it's integrated at the back of the storage. The cost is about €5. Okay, so the good thing is, if I have this installed, these 20 million fridges, I have an electric power capacity of 1.15 gigawatts. I can play with this capacity and have a storage capacity of 3.5 gigawatt hours. So it is something not bad. So now back to my questions. What is the benefit and of this dispatchable load? What is the value and who would pay for that? And now I think it's very interesting to look at different scenarios, different cases. So if I look at a country with a reliable grid, like Germany, so it is not very interesting for the owner of the fridge to have this asset in my refrigerator. And then therefore, it's not very interesting for the producer of fridges to install this. Nevertheless, one of the German producers of fridges was partner in this project. So we really did it. But there's no interesting business case behind it, I would say. It might be interesting for utilities, for grid operators, and in the end for the society, because this dispatchable load could allow to integrate more renewables than without this. But if I look now at another scenario, at a country with a weak grid, where I have many blackouts, so in this case, it is very interesting for the consumer to have this capacity and this possibility for a 7-hour cold production in my fridge, and therefore it is a very interesting asset for the fridge producer. And again, it's interesting for utility, grid operator, and in the end for society. So we have a totally different picture here, and that shows that sometimes, even if it's a good thing to do, it's not certain that somebody will pay for it. So that is, especially for the first case, it's valid. So now in our working group in the IEA, we try now to do this example as an exercise to put some number on it. So on the way from benefits to revenues to a business case. So what we proposed in this working group is that we have a way of visualizing like this, where we have the benefits, then we have the revenues, and then we have the cost of the system. So the benefits, from benefits to revenue, is the question: who would pay for that? So usually the revenues would be smaller than the benefits. And then we have the cost. And if the revenues are higher than the cost, of course, then it's a business case. And the other way around, if the cost is higher than revenues, okay, then it's a problem. So I try now to list all the benefits from this system, from this cold storage in the fridge. So the first thing was the one we had in mind when we started the project, the dispatchable load for grid balancing. So there's actually, it's interesting for grid operators because they have controllability, flexibility in the system. The second one is the uninterruptible cold supply. I mentioned it in the example of a country with a weak grid. Okay, that's interesting for the consumer because he has a security of cold supply. Then we have the topic peak load reduction. We could use this storage for this purpose. That's all would also be interesting for the consumer. Then we have the possibility of integrating more renewables, so reducing the curtailment and a higher renewable energy utilization. That would be interesting for renewable energy supplier, for utilities. And then the last point is we could do arbitrage. We could buy cheap and use it later with this system. That could also be interesting for the consumer again. So now I try to put numbers on that. Dispatchable load. We have a number, a cost for primary control power. It's 10,000 euros per megawatt. Problem is a little bit, fridge is in the range of 50 watts. So that means we make per year something like 50 cents. Okay, that's not a lot. The uninterruptible cold supply, though now I tried, it's very, let's say, very rough, this calculation. It only give you a hint. So the value for cold supply, what would be the alternative? It would be something like a fossil fuel-based generator. So in this case, we would pay 50 euros per kilowatt hour. The consumption of a fridge is in the range of 100 kilowatt hours per year. And we say 10% of the time we don't have an electricity grid. So that means we have to replace 10 kilowatt hours. So that would be 5 euros per fridge. You remember the cost of this unit was 5 euros. Okay, that's interesting. Peak load reduction. Peak load reduction is, in Germany at least, it's not possible for consumers, for private households. So doesn't work. Then we have curtailment reduction. So that means we could integrate more renewables. The question is a little bit how many charging discharging cycles for renewable surplus we have. So it's about 0.2 kilowatt hours per cycle, and I would say, okay, it's just an assumption, 50 times per year. So that would be again 50 euro cents. So it's very small. And then the last point, the arbitrage. If we say we have a difference in the electricity price of a factor of 2, so between 10 and 20 euro cents, so that means I could play with 0.1 euros per kilowatt hour. And I say 50% of the energy supply, I can deal with this. So then again, I would end up with 5 euros. So if I put all this now in this picture, you see the cost is 5 euro. The benefits are much more. And then we have these revenues. The curtailment reduction is very small. The dispatchable load is very small. But then we have arbitrage and uninterruptible cold supply. And the interesting thing that these two are interesting for the consumer. So that makes it easier because we have one target group. So you see that this is a very simple, I did it in a very simple way, probably too simple, but it shows a little bit how complex this evaluation of the different revenue streams is. And it shows again another point that what we need is a stacking of benefits. So that it in many or in most cases, a storage can do more than one thing. And that means we have to stack the benefits and we have to stack the revenues. Okay, so that was the first part of economics. Now let me come to the technologies. Technologies, we have a picture like this, which shows us electrical storage, chemical storage, and thermal storage. And within these three groups, we have many subdivisions. So I will, and then we have these cross-cutting approaches. So we can go for power to gas to power. So producing hydrogen and then by a fuel cell going back to electricity, or power to heat to power, high temperature thermal storage, which produces electricity at the end. Electrical storage is basically batteries, but it also can be pumped hydro and other things. Thermal, you see here, this is an example of an exotic system we developed in my institute. It's a adsorption zeolite storage, so it's a thermochemical storage. And chemical storage, it's all mainly based on hydrogen production. So electrical storage, electricity can be stored as electrical energy, but that's for, let's say, for a very small amount of applications and a very small amount of electrical energy, super magnetic energy storage or supercapacitors where you really store the electricity. In most cases, you store the electricity in an electrochemical system. So lithium-ion batteries and all kinds of batteries, also redox flow batteries. And then you can store it as mechanical energy. So that's the pumped hydro example, but it also can be compressed air, it can be flywheels and other things. Thermal energy storage, we have also different possibilities. One is heating up and cooling down a storage medium, so that we call sensible storage, hot water tanks, for example, underground thermal energy storage, things like that. The last years, we had a number of high temperature approaches here where we store heat at temperatures up to 1,300 degrees in solids and like rocks, things like that. Then we have the storage of latent thermal energy. So that was the example of the cold storage in fridges. It can be what we call phase change materials. So materials, they change their phase at different temperature. Ice is very known, that's at 0 degrees, but we can have phase change materials at 600 degrees, aluminium, for example, or we can have phase change materials at minus 80 degrees. We developed in my institute for the transportation of vaccination materials. So it's all possible. And then we have this thermochemical I mentioned already. So these are chemical processes or sorption, adsorption, or absorption processes used for thermal energy storage. And then if we look at chemical energy storage, we have electrolyzers producing hydrogen. And from this hydrogen, you can produce methane. Methane can be used as natural gas, or we can, from the hydrogen, produce synthetic fuels like LOHC or other fuels. So now we have this variety of technologies, and of course we have a huge variety of applications. And in the German Energy Storage Association, we try to list applications. So that's a list, but this is, of course, it's not not complete. So we said, okay, we have some subdivisions like renewable energies or energy efficiency. So the two columns of the energy transition. In the renewable energy, we have the integration of renewable electricity, which is very important because most of the renewables will come as electricity. So it's about grid stability, grid balancing, demand side integration. And then, of course, integration of renewable thermal energy, like concentrated solar power, solar thermal processes, and so on. And then we have the energy efficiency side, where we have industrial processes. Waste heat utilization is a big topic. We have the building sector, heating and cooling. We have electricity production or mobility. And now you can say, okay, we have these different technologies at hand, and you can identify some fields where certain storage technologies are the most suitable for the application. But I would go now into some examples. Some examples first with, I would start with energy efficiency. So that could be something like recuperation of mechanical energy by flywheel energy storage. So recovering the braking energy of trains. So what we need there is a high power in and output. So it's for a very short charging, discharging times in the range of 25 seconds. And it can really reduce the huge amount of electricity needed when the train starts again. So it's a reduction of peak power demand. Another one is, I showed you already the picture on the left. It's the thermal energy storage for waste heat utilization from industrial processes. So this one is actually, the waste heat can come from, let's say, foundries or let's say, waste incineration plants. So actually, this is a waste incineration plant where we collect heat at 135 degrees. And it's a mobile system. So we transport it here and can deliver it to another industrial process. So now the second column was the renewable energies. And here I have two approaches. The first one is renewable energy integration by distributed energy storage systems. So that was the title of one of our working groups in the energy storage TCP. So it was distributed energy storage for the integration of renewable energy, DESIRE. And we developed this kind of picture you see down here, where we have the renewable energy source, we have the consumer, we have DES is the distributed energy storage, and then we have either a grid connection or not. And these storage configuration, we collected them, and I will show you some examples. So here we have, for example, it's a building on one of the Austrian mountain tops, the Ostpreußen Hütte. So it's completely grid independent. So that's an example for the autarky, where we have a PV and battery system. And you see here in our pictures, solar PV is the source. It's a single home, has no grid connection, and uses a battery. Another example, this is from Canada, Drake Landon Solar Community, where we have a local district heating system, which is supplied by solar thermal collectors. And we really have a seasonal storage here, which is collecting heat in summer in a large underground thermal energy storage, and has a solar fraction of 90%. So that means 90% of the heating in winter comes from the solar thermal collectors producing heat in summer. So that's a very amazing value. And you see here, solar thermal is the input. It's a residential area. It has a grid connection for the missing 10%, and it had this underground thermal energy storage. So we collected over 90 of these configurations. Most of them are commercially available. about 40% of these distributed energy storage configurations were electrical storage, 40 were thermal, and 20 were power to gas, so chemical storage. They were all optimized for their local applications, so very strong connection to the local application, and the grid services were provided as an additional benefit. So next point for if I look at storage and renewable energies, is what we called flexible sector coupling. So this again is a working group, or it was a working group. It is just finished. So I will start now explaining what we understand by flexible sector coupling. First, we look here at the CO2 emissions caused by the actual demand side. So you see here space heating, for example, process heat, process cold, lighting, domestic hot water, mechanical energy. And here you see these statistical sectors: industry, private households, trade and commerce, and transport. We had to talk in this working group about sector coupling. What does that mean? So we defined 3 sectors. The electricity sector, which they are more or less demand sectors. So the electricity sectors includes everything which consumes electricity. This is important because, as I said, the main input from renewable sources, PV and wind, will come as electricity. So it's very clear for lighting, ECT controlling, but it also covers electric motors in industry, appliances in households, and things like that. The second sector is the mobility sector. This is about kinetic energy. It's about the transportation of goods and people. It's about everything from cars, trucks, trains, ships, planes, and so on. And then we have the thermal sector, heating, cooling in buildings and in industry, and process heat and cold, space heating, domestic hot water, so all the thermal needs, all the thermal demand. If I look now at the same numbers and have them structured following the electricity, thermal, and mobility sector, we see that the electricity sector is responsible for, let's say, about 1/4 of the CO2 emissions. Thermal is responsible for more than half of it, and mobility is responsible again for 1/4. So that means thermal and mobility are responsible for 75% of the CO2 emissions in developed countries. So now we developed this picture. We said we have the 3 sectors. We have the renewable energy input here on the electricity sector, and the sector coupling means now that we have to, let's say, deliver renewables to the thermal and mobility sector. The background is that in Germany we have here, we reach several times, or I think this year we were almost at 50% renewables in the electricity sector. But we have only about 13 to 15% of renewables in the thermal sector, and we have only about 8% renewables in the mobility sector. So that means it's very important to really bring down the renewables to these 2 sectors. But, and that is what we call flexible sector coupling, we have to integrate storage here. And I show you now some pictures we developed in this working group. Again, the 3 sectors. We introduce now here an intermediate layer, which is representing the storage technologies: thermal, that is chemical, and electrical, as I mentioned before. And that was a mistake. Sorry. Oops. I'll be right back. So here we are. Yeah. So this is this intermediate layer. And then we have storage technologies. I mentioned before, these technologies where they power to heat, for example, power to heat to power, or hydrogen fuel cell, or vehicle to grid, where it's in the end the output again is electricity, so it's not sector coupling. But then we have these pathways. We can go from electricity to thermal, and then we have the possibility to store thermal energy and not electrical. Here we can store the gas, the hydrogen produced, and that can be used for a hot temperature heat supply, or it can be used for mobility. And the electricity can be stored in an electrical storage and used for mobility as e-mobility. So what we have more flexibility because we can choose the appropriate storage technology, and it doesn't have to be a battery. Yeah? And that's very important because we have a price difference. Electrical storage is about 100 or more times more expensive than thermal storage. So it is, if it's heat we need, it's maybe the better idea to use a thermal storage instead of an electrical storage, and then to go from the electrical storage to the thermal. Okay, I will bring examples for that. So let me now come back to economics. You remember I said that the relation between energy storage and the application is very important. And here at the end of this definition, I said the economical environment, the expected payback time, the price delivered for delivered energy is determined by the application. So this is the basis of this approach I show you now. We call it maximum acceptable storage cost. It's a top-down approach. So we say we can define the maximum acceptable storage cost, the price per storage capacity installed, can be calculated on the basis of three facts: the expected payback time, the interest rate, and the energy cost. Here we talked, in our first approach, we talked only about thermal. We are currently working on to expand this approach on other things like electrical or even power energy per time. So one example, if we look in the building sector, the payback time expected is quite long, 15 to 20 years, and interest rate is in the range of 3 to 6%, can be accepted, and the price for energy for heating is in the range of 6 to 10 euro cent per kilowatt hour. So that is the price for district heat, for example. So with this, we use the annuity factor. So you don't have to go into details here. But we introduced now three economical environments. One I mentioned already is the building, where we have the interest rate in the range of 5% and the payback time. So I mentioned that. In industry, we have higher interest rates, but we have much shorter expectations on the payback time. And then we defined a third class, the enthusiast, so somebody who is not really interested in getting the money back. So 20, 25 years, he can wait, and the interest rate is 1%. Okay, so these three environments we defined, and then we came to this result here. So we have the maximum acceptable storage capacity cost. So that's a price per kilowatt hour capacity. It's on the y-axis, and you see it's a double logarithmic, so very, very tricky. And here you see our environments. And on the x-axis, you have the most important parameter we found, the number of cycles per year. So now we can do some examples. We talked about seasonal storage. So seasonal storage means summer to winter. In fact, in the real operation, it's not one cycle, charging in summer, discharging winter, because they are intermediate charging, discharging operations. So maybe it's 1 to 2 cycles per year, something here in this range. And it is for heating in the building sector. So this approach now says, okay, you can do that, but the price for your installed capacity per kilowatt hour has to be in the range of €1. So you have to build a storage with the cost of €1 per kilowatt hour capacity. Remember, lithium ion battery is 250, something like that. But in Denmark, the picture I showed you in the very beginning, this large hot water storage, that is in the range of 50 cents. So that means it's below this. It's somewhere here. And that is very interesting. As long as you're below these lines, very good. Another example, we have, let's say, an industrial application. So let's say this, the example I showed you, the mobile storage from the collecting the waste incineration heat, waste heat, with a thermochemical storage. So maybe one time per day. So then we are 2, 3, we are here, somewhere here, and we are in an industrial range. So we can afford a system with about, let's say, 40, 50 euros per kilowatt hour capacity. So this system actually is more expensive. It is more than 100. So that means it's somewhere here. It's above these lines. So it's not a business case as it was finished. Now, after the Russian invasion, we had much higher prices for heat. So that means today these lines went up and the system is now most interesting. So this is just to give you some examples how you can use this diagram. So the important thing is that we have a kind of range between these economic environments, a factor of 60. But most important is the number of cycles per year. And this is really something given by the application. And this can imply a factor of 1,000. So this is really interesting. Okay, so I come to the conclusions. We have a large number of energy storage technologies available and under development. So Halime and I, we are only two of many, many experts working in this field. So a lot of R&D is going on here. A large number of possible applications can be identified. So what I showed you is only a small, let's say, picture. Energy storage can support the increase of energy efficiency. I showed you some example. It is very, very important for the integration of renewable energy. This can happen through distributed energy storage system. It can happen through flexible sector coupling. The value of storage can only be quantified within an actual application. And I showed you some examples and how to calculate that. So the final message is always think energy storage within real applications. And then you really need all the technologies because we will find many, many real applications. With this, I would like to thank you very, very much for your attention, and I'm open for questions now. Thank you. I will close now this. Okay.
Thank you so much, Andy. Can you hear me?
Yeah, I hear you.
Okay. This was a really very nice presentation and very timely for Turkey, I should say. Yeah, thank you for accepting to join us for the series of webinars we are organizing with TTMD, not only showing what we're doing in energy storage and other TCPs, but how we can all learn and apply them in our works and especially in Turkey. I just want to start the question and answers session now, but maybe I start with a comment and a short question. The comment is on the fridge project that you have shown, the cold storage with PCMs. As you know, we also did that with a producer in Turkey, and I just had a meeting 2 days ago with them, and they already have a product that they are selling to Africa and Asia. So I
Very
will
good.
share
Very
with
good.
you later of the results of that. That's really nice to hear. And
Great.
my question is about a very current activity or a report that I have heard about that has been prepared by World Bank for Turkey. It's about the distributed energy possibilities in Turkey, and it's focused mainly on solar energy and battery storage. And when we say solar energy, it's PVs only. And here we heard from you that distributed energy storage could be much more than that. And could you please comment on that?
Yeah, yeah. Thank you very much, Halime, for the question. It's I'm also active in a initiative from the World Bank. It's called Energy Storage Partnership. And as you said, that started as a idea for bringing energy storage applications into developing countries. So the idea and what they had in mind is exactly as you said. It's PV in the battery. So I was at one of these meetings and I said yes, but look at take an example. Yeah, you look at a fisherman in Senegal or wherever. So he needs cold storage. He needs ice to keep the fish fresh. And so his system. He can install a lot of battery capacity to run the ice maker, or he can produce ice when the sun is shining, and the ice storage is keeping the cold over the time, and the ice storage is much less expensive than the battery. So and with this example, they started to realize that it's really first you have to look at the demand side, and then you have to choose the right storage technology. And you have a big advantage if you do that. Yeah. And but it's a long way. It's a long way, and because I agree that if you now look at this system I just mentioned in detail, you will find out that okay, it's still you need a small battery because yeah, it's better for the operation of the ice maker, for example. So and then it's getting it's not complicated, but it's not as simple as PV and battery. And this additional complexity creates some difficulties.
Okay, thank you very much. Now I'm looking at the questions. We have some good questions. The first one is to bring down the renewable energy to the mobility sector. It can be either storing electricity as battery storage for electrified transportation, uh, using electrolyzer and generating hydrogen for fuel cell vehicles and hydrogen combustion. Which way do you think is more feasible with better energy storage feature? So for mobility.
For mobility, yeah, I think mobility is a big word, and it covers many different technologies. And I think um, um, there also you have really carefully look at the actual application. So I think everything with cars. So electric mobility with a battery is a very good solution because it's very efficient. The whole chain is very efficient. On the other hand, if you look at aviation, yeah, I think the future will not be a battery airplane. So there it is very important to go into efficient, let's say, synthetic fuels produced from solar energy. So it really depends on what you're talking about, and I think it's today, and especially in Germany, I can tell you, it's a kind of ideological discussion, which makes it very difficult. I think efficiency should be in the focus, and the possibility if you can do it. Um, in Germany, it's a question of the old world, the car manufacturers, combustion engines against the let's say the electrical e-mobility, and that's not helpful. I mean, the discussion has to be really on things like efficiency. Yeah.
Yeah, the question was from Nader Javani, so I forgot to give the. Thank you very much for your answer. And the next one is from Jenny Ekman. On the fridge topic, there is a positive possible gain for customer, but would a customer really be interested if the gain is €5 per year?
That's a very good question. Thank you for that one. Yes, I agree. um, um, I think this example, that's why I like it, because it really is at the limit of possibilities. Yeah. Yes, you're right. €5 are no reason to buy something or not. But I like the idea that in the future we will have an intelligence behind all these electric assets in our household, and we can control them. And this is a huge possibility for the, let's say, in the end, for the control of the electricity grid, and therefore it might be needed. And if you have the possible, in this context, the arbitrage, nobody would do that for €5. No, nobody. But this availability of a cold production when you have a blackout, that is valuable. I think this is a reason why people would buy this fridge.
Thank you very much. The next question is from Anthony Gil. Hi, Anthony. It's nice to have you with us. My question is related, he says, with the distribution of carbon dioxide emissions. In my opinion, emissions on thermal and mobility have a huge component based on the efficiency of the process itself, 30 to 60%, compared with much higher efficiencies of electricity sector. Am I right? If yes, thermal energy efficiency is a problem to tackle, not only integration of renewables.
You are right. I don't know. From these numbers, you cannot see really how much potential you have in the increase in efficiency. But I showed you examples where energy storage can work in this increase in efficiency. Yeah. But it's true. It's true. This is a picture of today. And of course, if the buildings are more efficient, better insulated, and the let's say the industrial processes are, let's say, more efficiently designed, if waste heat is recuperated and so on, of course, yeah, then these numbers would change. Yeah. But energy storage would play a role in this. Don't forget that.
Yeah. So it's better to have efficient processes at the beginning, of course, but yeah.
Yeah.
The next question is from Ole Jacobs or Dahlen, and he says, nice structure for the economics of energy storage. Do you also have methods for taking also the time aspect into consideration? For example, using energy storage can solve grid congestion challenges much faster than cheaper alternatives like grid upgrading.
Yeah. Yeah, this is exactly so. We are more at the beginning of this working group, but this is exactly the point. We have to compare storage solutions to other possibilities to solve this problem, yeah, we also collecting different, let's say, methodological approaches. But this is ongoing work. But you're very welcome to join us. So you have seen this. Halime showed you the link to the ES TCP, and of course everybody can join us in this activity. We are looking for, because we definitely need financial and other experts. We are more the technological people, and it's good to have other aspects and other views on this integrated.
Thank you for that response. And the next question is from Barış Brak, his Technical University of Denmark right now. The electricity market prices are dynamic in the EU region. How should we take the dynamic prices into account for the economics of the storage? With renewables, which have flexible demand and supply curves, the dynamic electricity prices bring another challenge to the economics, especially when we combine the storage options with lower other low carbon solutions such as heat pumps.
Yeah, there exists a very good example. We had in the late 90s, we had very huge price fluctuation in Japan. So it was about 6 times more expensive in the early afternoon, where all the air conditioning systems are running. And so they had a difference 1 to 6 in the electricity price. And that really pushed storage technology. For example, in the station of Nagoya, we had Halime, I think you visited it all also, right? There's a huge latent cold storage system. It's really huge in the basement of a huge skyscraper, and they really they charge the cold storage at low price times, and they did the air conditioning from this system in the peak hours price wise. So that means price differences are a huge, let's say, motivation for storage. And I think price differences, we have this discussion in Germany. You know, we have a lot of wind in the north, and we have a lot of industry in the south. Especially Bavaria is very keen on having no price differences in Germany, yeah, because we don't want in Bavaria they don't want wind turbines because we have a very beautiful landscape, and they expect an upgrade of the electricity grid to bring down the cheap wind electricity to Bavaria, but it will end up at least to price zone, yeah, and that will change the picture.
Yeah, we have in Turkey a tariff for 3 different time frames, and I'm not sure we are making much use of that in terms of energy storage right now, but that's also potential.
Yeah, I mean,
Yeah, the next question is from Sergey Barsky. He is asking, do you know about any projects regarding heat pumps, energy storage, thermal or electric, for residential sector, optimization of heat storage? And in parentheses, he says, not PCM.
so I'm not sure whether I understand correctly, but you want the heat pump and the storage, or
Yes.
Okay, yeah, heat pump and storage is that's one of the pathways I showed you in the sector coupling picture. So it's electricity converted into heat and stored at the thermal site. So that's a very power to heat, you can call it. That's one of the best options, I think. Now you have to talk about efficiencies and if you do all the heating by electric-driven heat pumps, of course you will have a raise in the electricity demand. But I think, nevertheless, that's what we have. Renewable energy sources are mainly electricity, and that means it's very useful to use this for the heating demand, which is the biggest demand. Yeah.
Yeah.
And yeah, sorry, this not PCM. I agree. The wonderful thing is, if we talk about the building sector, So the temperatures are usually below 100 degrees, and therefore water is very, very good. So a hot water tank is a very good thing
If you have the space for it.
if you have the space for it. And if you have water, water is also yeah, not always available. Yes, yes.
Yes, yes, thank you. And if the next question is from Yalcin Yalaki. He wants to know how much overlap is there in electricity, thermal, and mobility sectors of energy demand?
Yeah, if I understand the question correctly, it's so yeah, it is a kind of tricky thing because if you try to separate these sectors, there is of course there is some overlap. But I think the basic things derived from these statistics they are valid. So there might be some overlap. You're right. It's not a very it's not strict these separations, but I think it's true. It remains true that the thermal need for heating, cooling, especially in industry and buildings, is the main demand we have.
Thank you for that. The next question is Paul Fritsch is asking, saying hi to you. And do you have other, well, the beginning is for keeping the focus on the application of the storage systems, do you have other positive business cases than the Danish thermal seasonal storage system?
Um, yes, yeah. I think there are some. And that's exactly what we try to identify in one of the subtasks of this new activity on economics of energy storage in the ES TCP. So we really want to have a list of successful business cases. So I can tell you one because that's one of my institute and my favorite, my personal favorite. So it is also it's very similar to the fridge, but it's in a dishwasher now. It's also a thermochemical storage in a dishwasher. Very small, 1 kilogram of material is in there, and it reduces the energy, the electricity consumption of about 25%. And that is we calculated that, and that is a business case, and you can buy this dishwasher since 2011. So it is a product. So there are many possibilities apart from the very discussed ones like batteries, large batteries for primary frequency control in the electricity grid, for example. So that's one of the things always in the focus. And there it's difficult. And maybe another finding from this working group we had at the last meeting, I found it very interesting because I never thought about this. It is also connected to this primary control storage application. That if you install storage capacity in the electricity grid for this purpose, so you will reach at a certain point kind of saturation because then you have installed flexibility in your system solving this problem. Yeah, and then maybe with the increase in renewables, you might need a little bit more, but it's not like this is a market where you can always produce storage and put it into the market. So you will have saturation at a certain point. That I found very interesting because I never thought of that.
Yeah, thank you for that. And we see, yes, there is one last question from Basam Taki. Suppose there is no renewable energy. Is it feasible to install energy storage?
Um, yes, of course. I mean, you remember maybe the right side of the picture of the list of applications that they were on on energy efficiency. So, example, waste heat. Yeah. So we have installed a storage in a foundry, iron foundry. They have a big oven to melt down the iron. They have waste heat. We collected the waste heat. So the oven runs on gas, natural gas, not renewable at all. But the waste heat we could collect. We can at 230 degrees. We could transform it into cold by an absorption chiller, things like that. So you can do that. Yeah. And I mean
Yeah.
also uh, it's not necessarily connected to renewables. But on the other hand, if you want renewables and if you want a high fraction of renewables in the system, then they are very important to storage.
Yeah,
That
I
that
think
was a good final word.
yes, I think so too. And I think don't have any more questions. Yeah. And Paul said he had already bought a dishwasher with zeolite based directly on your enthusiasm during a previous visit to your institute. Yeah, that's nice to hear.
Thank you.
Let me see any other comments, questions. No. Okay, so thank you very much again. Andy, do you want to give some final comments or?
No, I'm very happy to have the possibility to talk to you all. It's always difficult that I don't see anybody, but I hope you're all there. So thank you for listening, and it was a big pleasure. Thank you.
As we had a very enthusiastic participants that gave us very good questions. Thank you for your participation, and thank you, Andy, for this very nice presentation. I think we can see that energy storage can be affordable, and also it should be considered in all cases of renewable energy if we want to make more value out of our renewable energy source. And if we, especially if we want to triple that renewable energy generation within the 7 years that are in front of us. Thank you all, and goodbye, and thanks again, Andreas, Hauer, and
Thank you very
TTMD.
much.
Bye.
Thank you. Bye bye.
Bye.